So just a quick video tonight, because it always amuses me when I read comments by flat earthers claiming that pilots are taught to fly across a flat earth. No, that is completely wrong. This is a manual titled Global Navigation for Pilots, International Flight Techniques and Procedures, and one of the authors is a PhD. We just need to look at a few pages to realise that navigation and flight planning is all based on a globe. Here's a section on great circles and small circles, the latitude and longitude coordinate system. Chapter 3 talks about maps and charts, how the aviation charts are produced as projections from a globe. It describes each of those projections, and there is a summary here, including the AE map, which a lot of flat earthers claim is the shape of the Earth, but it's actually just a projection from the globe. We can then skip ahead to celestial concepts, because flat earthers seem to love talking about sextants these days. You can see that celestial navigation, again, is all based on the globe. And there's a circle of equal altitude, and two of them working just fine on a globe. So sorry guys, if you're a flat earther, buy this book, read it and So in this video we're going to look at how aircraft follow the curvature of the Earth, and that this is achieved by simply maintaining altitude. I have addressed this topic already on my channel a number of times. To follow the curvature of the Earth, an aircraft just has to maintain altitude. How easy is that? No descending is required. I'm seeing videos and comments by flat earthers claiming that aircraft have to descend to follow the curvature. Nothing could be further from the truth. The correct way to follow the curvature of the Earth is to maintain a constant altitude, and that means no descending. And this is really just basic geometry. It's so simple
a child could understand it. If we have a basketball and we put our finger 1 inch above the basketball and we maintain that distance of 1 inch as we move around the basketball, we are following the curvature. We are not getting closer to the basketball, we are keeping that distance of 1 inch, and by doing so, we are following the curvature. And it is the same with an aircraft. Here is a diagram you may remember from a recent video. We see the curvature of the Earth, and we see this line representing the intermediate segment minimum altitude. You will notice that that altitude is curved also, because it is equidistant at all points from the surface of the Earth. If we are flying at 40,000 feet above the surface of the Earth, and we fly for 1,000 miles, maintaining 40,000 feet above that surface at all times, we must have followed the curvature. So for the aircraft to follow this constant altitude line, which is curved, there is no descending required. If the aircraft descends, it is not maintaining altitude, it is getting closer to the ground, and if it continues descending, it will hit the ground. To follow curvature, no descending is required. So when we fly our aircraft, we select the assigned cruising altitude, and there you can see 41,000 feet. That is the indication of the selected altitude. It doesn't matter if we are hand flying the aircraft or if it is on autopilot, the objective is to maintain that altitude. So as you could see very clearly, the aircraft is making constant small corrections to maintain altitude precisely. That is all we need to follow the curvature of the Earth, to maintain a constant altitude. So today we're going to look at one of my favourite topics, and that is real aircraft flight plans, because they irrefutably prove that the Earth is a globe. What you're looking at here is a sign on a building in Adak, Alaska, and in this photo you can see myself and my friend Marcus reviewing a real aircraft flight plan while we were refueling in Adak, Alaska. At the time we were ferrying this small citation jet from the USA to Australia. And if you're wondering where Adak, Alaska is, it's here on the island chain to the west of Anchorage, just before you cross into Russian airspace. Now why did we go via Adak? Because these small jets don't have the range to make it from mainland USA to Hawaii. So you need to come up through Canada, Alaska, across Russia, down through Japan, Korea and Indonesia, and back into Australia. I'll share that route in more detail later in this video. So, real aircraft flight plans, the topic that flat earthers are afraid to touch. Why are they afraid? 1. Because a proper analysis of a real flight plan will prove it is calculated for a globe. And we're talking about real aircraft flight plans, a flight plan that a real pilot can use in a real aircraft to fly around the Earth. And here is what the route looked like from Brisbane up to Hawaii. And this image shows us the cloud that we can expect to encounter during the trip. If we go back up to the main body of the flight plan, this is where it gets really interesting and very bad for flat Earth. Here we have the waypoints on the left hand side. Each waypoint is defined by a precise latitude and longitude. We can see the wind, here it is 090 degrees, 19 knots, and the component M018 means minus 18 knots. That means the component of the wind was giving us an 18 knot headwind. The S represents the severity of turbulence en route. We have true airspeed, 486 knots, ground speed, 451 knots. Magnetic game over. We can prove that the distance between any two waypoints on any flight plan used by any aircraft flying around the Earth is irrefutably calculated for a ball Earth. Let's look at this example. Atras to Akumo, 283 nautical miles. We have the precise latitude and longitude of each of these waypoints, and we can apply those to a spherical trigonometry formula to determine what the distance is calculated for a ball. And the formula we can use to prove that flight plan distances are computed for a ball is called the Haversine Formula. And the way this works is to calculate an angle in radians from the center of a sphere between 2 points on the surface. Here we can see point A to point B. They have an angular separation measured from the center of the sphere. What the Haversine formula does is calculate that angle in radians. Now, if we consider a unit sphere with a radius of 1 unit, if that angle is 1 radian, the distance between the points on the surface will equal the radius of the sphere. And that is key to understanding how this formula works. Now, for a previous video, I created this simple great circle distance calculator which uses that formula. Here is the formula in cell C10. You can see it up in the top bar here. This calculates the angle in radians between 2 points on the surface of the Earth. We then multiply it by the actual radius of the Earth to get a distance in kilometers, which we can then calculate to statute miles and nautical miles. And here is the formula. Now remember, this part of the formula that I have highlighted simply calculates the angle in radians from the center of a unit sphere between 2 points on the surface. That part of the formula has no idea about the size of the ball or how far the actual distance is. We then need to multiply that angle by the actual radius of the sphere to get an accurate distance. And here you can see we are using 6371, and that will give us a distance in kilometers. I could use the number 3959, and that would give us an answer in statute miles. So let's take a look at our flight plan pair. Between Atras and Akumo, the flight plan distance is 283 nautical miles. The location of each waypoint is given here in latitude and longitude, and the format is south 09 degrees 48.8 minutes, east 172 degrees 27.7 minutes. When we convert those values to decimal degrees, we have these figures, and when put into our calculator, you can see it results in a distance of 525 kilometers, which calculates to nautical miles 283.6. The flight plan distance, 283 miles. So you can see it matches beautifully. You can choose any pair of waypoints on any flight plan and run it through this simple calculator, and you will see that the distance here in nautical miles matches the flight plan distance. And we can use this same formula to verify that the distance between any two waypoints on real aircraft flight charts matches the calculation for a ball 6,371 kilometers in radius. Let's take a look at this South Atlantic chart. And here is the chart opened up, and you can see a route from Ezeiza in Buenos Aires to Cape Town, Africa. It's a non-stop route across the South Atlantic. Now this alone debunks one of the flat earth claims. This is a real aircraft flight chart, and we can see very clearly that we have a route marked. Now each of these waypoints has a specific latitude and longitude, and we have a distance between them. If we plug in those values into my small calculator, you will see that the distances between each waypoint match the calculation for a ball 6371 kilometers in radius. So let's try it between these waypoints, Morsi to Moons, showing a distance of 457 nautical miles. And here we can see the coordinates for Morsi and Moons, giving us a distance of 457.76 nautical miles. So again, agreeing nicely with the distance shown on the real aircraft flight chart.